Okay, so we begin this lecture with shifting our attention from what we are looking at in the last couple of lectures of range searching. So, we have only done part of range searching, which is orthogonal range searching. There is a part of range searching which is more general, there is more general kind of ranges other than rectangular ranges, and that will be covered by Professor Agarwal at a later stage. And these two topics, although they all are both are range searching, they are kind of disconnected. I mean, the techniques that we use for the general range searching is not going to be very similar to what we have done before. So, what we have done in the context of orthogonal range searching, whether it was 3-sided or the 4-sided, the solutions were primarily data structure related, right. So, the performance that we got out of these space for pre-processing time, etc., were mainly dependent on the way we define the data structures, whether it was KD trees or it was the range search trees. Now, when we look at the general range searching, well, they will have some data structures, but you'll have to use some more deeper, let us say partitioning techniques which use random sampling and geometry. Right. So, there will be somewhat different, overall scheme will be the same. You will have to again resort to some kind of canonical partitioning, but that canonical partitioning has to be of a kind where when you are dealing with a general kind of a range, again it should not intersect too many of those canonical partitions. Eventually, the query time depends on the number of nodes that you visit in the data structure, which is essentially the number of canonical partitioning that this range intersects. Okay, that is the overall thing. So, but for the more general case, that partitioning uses some very sophisticated techniques actually. So, today I will start on a topic which is somewhat different in spirit from what we have been doing so far, and although I never explicitly discussed this aspect, the algorithms that we designed had essentially the running time or space or whatever the performance bounds were expressed in terms of the input size, maybe the input size and output size, okay. Some kind of combinatorial expression on just, I mean it is just a combinatorial expression, right. Now, the input size is a combinatorial quantity, the output size again is a combinatorial quantity, but we did not have anything that depended, let us say, on the slopes of the lines or something that is geometric in nature, which may be a property of the input objects, but we did not want to sort of make our algorithms dependent on that. And simple example would be that if we make our algorithms, we could let our algorithms depend on the size of the numbers. Okay, that would be one departure or deviation from this model. So for instance, when we did the, let us say something like your segment tree in data structure, we were always trying to partition these on the basis of the size of the input, right. We want about half the points on this side and half the points on that side. But someone could also think about why don't we partition on basically the coordinates of the points, right. Look at the largest x coordinate and look at the smallest x coordinate and sort of divide on the basis of that interval. So, we are going to then divide the interval, but in dividing the interval we may not actually divide the input, right, because things could be. So, what I am saying is, suppose we have the spread of the points is like this. Okay. Let me take a bad example actually. Okay. And this point is kind of way out here. Okay. So, we were always trying to divide using some kind of median partitioning line, which divides the input set of points into roughly equal parts, about n/2 and n/2. Okay. The other option could be I take the x min, x max, okay, and whatever the values are, okay, I look at the median of that and use that to partition the set of points. Now, in this situation, as this example shows, it may not actually have the effect of dividing the input set. Okay. But nevertheless, there is some partitioning that is happening, and the partitioning is happening essentially on the coordinates, okay, or the size of the numbers that are being used in the algorithm. And one could again define, let us say, a segment tree or a range tree, okay, just based on this kind of partitioning. But then when you do the analysis, what will show up eventually is some number that will depend on. So, let us say r equal to x max minus x max minus x min. Okay. So, it could depend on this x max minus x min, and perhaps another. So, we keep on partitioning, but we will keep on partitioning till we have we eventually end up dividing the points, so that points appear in only one vertical slab. So, we will have to keep dividing, because eventually whatever query algorithm we run will be run on that basis. But then the number of divisions that we require here will depend on some kind of a ratio between the maximum separation to the minimum separation. Do you agree with that? So, this is the maximum separation I am calling big R, and the minimum separation could be some small r, okay, which is, let us say, defined with the closest pair. Okay. And I claim essentially, if you divide it this way, okay, then your algorithm will have some kind of dependence on this ratio. So, this is also sometimes called as the spread. It is maybe I should not say x max minus x min, but something like the diameter is a better measure of that. So, this is only in a very simple case, but usually it will be the diameter, the 2 points that are furthest apart. So, the ratio between the 2 points that are furthest apart divided by the 2 points that are closest, okay, is what defines this thing called spread. Okay. And if you do your partitioning based on this on the coordinates, okay, then it will have some kind of a dependence, like roughly about log of this, because you keep dividing till the points that are closest must also fall into some different intervals. Right. So, this will be again some kind of geometric algorithms, okay, where you have an explicit dependence on the values of the coordinates that are input. Okay. And this kind of algorithm is actually very common in practice. Okay. I would actually go as far as to say that people who do not study geometric computing or computational geometry formally, they often resort to this kind of algorithms. Okay. And often it also works reasonably well in practice, otherwise they will be concerned and they will actually then maybe consult someone who understands these things better. The algorithms turn out to be simpler, okay, and often work well in practice, because this this point set that I just drew, okay, this is a bad point set because it is sort of clustered somewhere, and the 2 points and a few points are very far apart. Okay. But if they are kind of uniformly distributed, okay, then this methodology where you are actually dividing on the basis of coordinates, okay, would work reasonably well. You can provably well actually in some sense. Okay. So, in many cases, because the input set is not that bad or not that skewed, okay, even when people use this kind of thing, it is like this. If you had not done this course, you would have probably thought about designing algorithms based on this kind of things. That is what it is. So, intuitively you are doing fine, but then when it comes to sort of rigorous analysis and looking at the worst case, then it may not work well, because R may be much larger than small r, much bigger than the ratio n that we are talking about, right. We are looking at log of n kind of things, and here you are looking at log of phi kind of things. So, in cases where this quantity is much larger than log of n, or that basically phi is much larger than n, which can very easily happen, right. It is basically the two values, the ratio of the two values can have ratio much larger than n, an exponential or something like that could very easily happen, right. I could have the largest separation as 2 to the power n, the smallest separation could be some few some constant, and then you are talking about a ratio of n rather than log of n. Right. So, things could go out of hand in some pathological cases. Right. But actually, for the next couple of lectures, I have decided to pursue this method a little bit more, and in the context not of exact algorithms, but in the context of approximation algorithms. Okay. And these approximations are not really approximations of hard problems. These are problems for which one can design polynomial time algorithms, but uh, primarily, we have great difficulty dealing with higher dimensions. Okay, the moment you take this convex hulls, range searching, Warner diagrams, etc., into higher dimensions, that the output size and everything sort of behaves sort of increases exponentially with dimensions. Okay, so when you go to higher dimensions, okay, we may not actually have the computing power to compute the exact convex hulls or exact Warner diagrams. And whatever structures we have developed in the lower dimension. Okay, although theoretically they are very clean structures, they give you optimal performance and so on and so forth. When you go to higher dimensions, because of this exponential dependence on D, you very quickly, maybe after about 5, 6, 10 dimensions, you would give up on those methods. Okay, and then think in terms of doing something, sacrificing something in precision, that is basically resorting to some kind of approximate answers. So, let me give you one quick example, what kind of approximations we are talking about here. So, think about this problem. It's a very, very fundamental problem, that is build a data structure for nearest point query. Now, this is the motivation why we came up with a structure like Warner diagram, right. We build a Warner diagram, build a planar point location structure on that, then we can, given any arbitrary query point, we can report the nearest neighbor very quickly. Right. Now, because I said the Warner diagram, the complexity of Warner diagram increases exponentially with higher dimensions. So, building or maintaining, and often these are done in a dynamic setting, building or maintaining the data structures becomes a nightmare, and no one would ever try that. The space, the moment space goes exponential, okay, because the Warner diagram itself is is going to grow exponentially in space. Okay, sorry, exponentially in the space will grow exponentially with dimensions. You cannot afford to even think about storing that kind of data structure. Right. So then. One compromise we can make is that instead of looking for the exact nearest point to a query, okay, we can think in terms of what are called approximate nearest neighbors. Okay, and what's the approximate nearest neighbor? So, approximate nearest neighbor will be actually parameterized by something called epsilon. Okay, let us call it epsilon, approximate nearest neighbor. So, given a set S of n points, not the, I shouldn't say, let's say the, I should say A, okay, an approximate epsilon approximate, an approximate neighbor of some arbitrary query point Q is a point P in S such that the distance between Q and P. So, let me write just distance, right, is less than or equal to 1 plus epsilon times distance between Q and, well, if I can use this notation, do you understand this notation? This will be basically the minimum distance between Q and S, the set S. The distance between a point and a set S, okay, let me, so I may be using this later on. So, this is basically min over all points, let us say T in S good, it has become brighter. Right. So, analogously, let me, since I have brought out this using this notation. So, distance between, let us say, 2 point sets P and Q, okay, is also defined as min over all pairs. P belongs to P, Q belongs to Q, distance. So, this is a metric basically for given 2 point sets. The minimum distance between the 2 point sets is basically take the closest pair of points where one point is in this set, the other point in the other set. Right. So, the epsilon approximate the epsilon approximate nearest neighbor is any point, okay, which is within that 1 plus epsilon. So, epsilon you can define, it is a user defined thing. So, if I want something within 2 times the distance, epsilon equal to 1. If I want something within 0.5, 50% of the closest neighbor, then it should be 1.5 times. So, just to give you an example, I have this set of points okay, and I have a query point, let us say this is my query point Q. Okay. Clearly, this is the nearest neighbor, okay. But then I am, if I use, let us say, epsilon equal to 1, okay, I am allowed to go as far as twice the distance. So, if you take this distance, okay, increase the radius by a factor of 2, any of these points would satisfy the definition. Okay, so I think the reason why this may work out better in terms of algorithm may not be immediately clear, especially when you are talking about higher dimensions. Okay. This is something that maybe it will come out in the next few lectures. I may or may not be able to get as far as approximate nearest neighbor, but I will define certain basic data structures which is used to compute these kind of quantities. Okay. So, approximate nearest neighbor is a very active area of research, and I think still continues to be to a large extent. So, this is just a motivating example, why one looks at approximations for. No, I am not reporting all of them. I am reporting any of them, any arbitrary. So, any of these points in this disk can be reported as an nearest epsilon nearest neighbor. I am not going to report all of them, certainly not. Okay. So, another example is it is a very practical, very famous problem. Just wondering, should I? Okay, let me just mention it. I may not be able to give you the full details of that. It's called the it's in the literature it's known as n-body simulations. Okay, so what's an n-body simulation? So, an n-body simulation is you want to you have a physical system. Okay, maybe think about the solar system or some part of the universe. Some basically some. It could come up in astronomy. It could come up in some kind of let us say modeling of some kind of molecular process. Okay. So, at macro or micro level, whatever, you have essentially some kind of bodies which interact using some forces, could be gravitational forces, could be electrostatic forces, magnetic forces, whatever. Right. So, you have these bodies or particles, whichever, whatever you call it. Okay. And when you simulate the evolution of this system, okay, where there are essentially some forces acting on these bodies, they will move or they will move in a certain direction. Okay, they will evolve in a certain direction. Right. So, and to do that accurately, you would like to probably or the most accurate modeling will be to compute all pairwise forces, right? Compute So, and there are, if there are n bodies, they are basically capital N choose 2 pairwise forces. Okay. Well, I mean n could be very large, okay, fine. N choose 2 is still a polynomial. Okay. So, if you only bothered about polynomial versus non-polynomial, this is not an interesting case. But when you do simulations, you want to simulate over many steps. Okay. So, if you can bring down this N choose 2 kind of, so each step I need to compute these pairwise N choose 2 pairwise forces. Okay. So, each step will take me about quadratic time, and if I want to simulate it for the next billion years or some such thing, this becomes substantial. Right. So, you want to do these updates. So, what happens? These are simulations over discrete time steps. Okay. So, we simulate for the next nanosecond, okay, and then find out the new positions and then simulate. Of course, there is a lot of error involved. Let us not worry about the errors. Okay. So, we are going to simulate it over many steps, and for each step, if you require this much of computation, okay, you are clearly being slowed down. So, let us say n is about 1,000,000, and if you are doing something like N choose 2 computations for each step, so it is a million times million computation, and if you can, let us say, cut it down by whatever 100 or 1000, perhaps even a million, whatever, then you can do that much more simulation. Okay. Either you can do that much more time steps, or you can do that much accurately. So, you can why nanosecond, why not a fraction of a nanosecond, because the more finer your simulation time steps are, the more accurate the results are. Okay. So, either way, either you do it more precisely or you do it for a longer time, it makes a lot of sense to try to somehow cut down on this computing all pairwise forces. Right. So, one technique that people have used very successfully is when you look at all these particles, okay, you may not, instead of computing the pairwise forces, this particle, for instance, okay, is kind of far from all these particles, okay, and I could compute the the pairwise interactions between this and all these particles, okay, but because they are a very large distance away. So, let us say this distance, minimum distance from this to this set, okay, is some distance d, and all this cluster, let us say, is within let us say is d over 100 or some such thing. So, what I am saying, the diameter of this cluster is much smaller than the distance from this point. Right. So, what would you do in such a situation? Yeah. So, whatever, whether it is gravity or some electrostatic charges, you will probably replace the whole thing by some center of mass or center of gravity or center of electrostatic forces, and that actually the technical part of it is can be worked out using some kind of Taylor series. Okay. So, we will not get into all that. The observation that we are making is that if a whole set of particles is kind of far away, okay, then we can approximate, okay, the interaction of all these particles by a single particle, essentially, because the difference between the interaction of all these will be very small, okay, and it depends on, again, what kind of error the simulation can tolerate. Okay. And if you can do that, then there is a chance that you can save a lot of these pairwise interactions. Okay. To give you one concrete example in terms of geometry, I will not calculate forces. So, suppose I have 2 points A and B. Okay. I want to compute the nearest neighbor. Okay. So, for a query point, it is just a very trivial case, of course, that I want to compute given any query point which is closer, is A closer or B closer, okay, and I can do it. It's the perpendicular bisector or whatever I do with the Werner diagram. Okay. Now, as this point moves away further and further, okay, what happens? The distances from this point to A and B becomes what? They become the distance between, they become not very different, right. So, if you move very far away, okay, this distance, let us say d1, and d2, okay, I claim that the ratio of d1 and d2, okay, decrease, well, I mean decrease, increase, either way, I mean they become very similar. If so, this is d1 is greater than d2. If I am saying d1 is greater, either d1 is greater than d2 or d2 is greater than d1, either of them. Okay. So, that decreases as x moves further away. In fact, we can even quantify it. Okay. If the let us say the separation between A and B is, let us say, t. Okay. So, if that is t, then at a certain distance, so this is t, right. So, we can claim that by triangle inequality, right, by let us say d1 is less or equal to d2 plus t, right. Okay. So, the question is that if you are looking at some kind of approximate nearest neighbor, okay. So, if we are interested how far do we go before A and B become indistinguishable. That is, I can report either A or B as nearest neighbor without and staying within this approximation factor. So, can you do any quick calculation on that? So, what I was saying is that d2 is less than d1 plus t. So, what you are saying is d1 is greater than t by epsilon. So, if d1 is greater than t by epsilon, then d2 is, we are saying that d2 is further apart. Okay. So, either d1 is further apart or d2 is further apart, right. So, if the minimum distance, I think what you are saying is the minimum distance is at least t over epsilon, right. So, min of d1 d2, is that basically what you meant? So, if min of this is this, what can we say about the max? That is what we are interested in, right. I want to report either of them. Can we claim this? Can we claim this? So, d2 is, suppose, just take an example, d2 is, suppose d1 is exactly the minimum of that is exactly t over epsilon, right. Let us say that is d1. Okay. So, then this is less than t over epsilon plus t, right. It is not working out. Okay.
So it's equal to T by epsilon into 1 plus epsilon.
Yeah, the better way to write it, right? So we should write it in a different way. T by epsilon 1 plus. Right. So, and you can verify, if it is larger, it only becomes better ratio. Right. So, if you look at this figure, I have this again. Let me draw the figure. You have these 2 points A and B. Okay. So, one way to think about, so this is the perpendicular bisector, right? So, as you, so you can think about basically the points is either on this side or that side. So, you're actually growing these balls, right? Okay, at some point they meet, that is basically the perpendicular bisector, right? And as these balls grow larger and larger, okay, and so outside of a certain region, basically both these points kind of have similar distances depending on the epsilon. Okay, you choose a smaller epsilon, you have to go further apart. But that after a certain distance, basically, after a certain distance, the minimum and the maximum distances are very similar. Okay. So, it has got something to do with the diameter of the point set. Okay. So, here I took 2 points, you can extend the same thing with the diameter of points. I could have a whole cluster of points. Okay. So, now I could add another point, and then again this will also add something, and then if you take a larger radius outside of that, all these 3 things will kind of look alike. So, it is basically something to do with the diameter of this point set, okay, and the actual closest neighbor. Right. So, you can the same kind of calculation will work out. So, what is happening is that as you move further apart, I mean from some set of points, okay, I do not need to maintain the exact Werner diagram or whatever the partition defined in the Werner diagram. Now, after a certain distance, I do not need that Werner diagram kind of, it is like saying if I am really very far away from all the points, I do not care about the partitioning there, although in the actual Werner diagram there will be some partitioning of the space, but I do not care about it because now I am only looking for an epsilon nearest neighbor. So, this is another example of this kind of computation. Okay. Let me give you my last example before we start looking at this problem in more detail, and that is the notion of what is called a spanner. Okay. So, given again n points, given a set P, with the Euclidean d dimension, okay, we define a graph G where it is a weighted graph actually. With the set of vertices is the set of points. So, I am writing P, okay, and some weight function. Okay. E is some set of edges. This is a weight, it is a weighted graph. Right. Such that for any p q in the set capital P, the distance between the Euclidean distance between P and Q, okay, so can be approximated by this graph basically. So, let me write d of G P Q. So, okay, the distance in the graph must be at least that much. Okay, we do not have any contractions. and it is guaranteed to be sorry, I am using t. So, t times strictly greater than 1, let us say. Right. So, the distance could get dilated in this graph, right, but it will never get expanded. So, you look at the path. So, the graph has the points of p as the vertices, okay, and there are some edges. Right. Of course, if you do not have any edges, then the distance become infinity, and that is not consistent with the definition. So, we will have some weight, and in fact, it must be a connected graph. Otherwise, there will be some point, some pair of points which is not connected in the graph, and therefore, the distance becomes infinity. It cannot satisfy this bound t. T is not infinity, t is some bounded number. So, it must be a connected graph, and moreover, if you look at the shortest path in that graph between p and q, it is no more than t times the Euclidean distance. Right. So, that is the notion of a geometric spanner. There are equivalent definitions for just general graph spanners. Okay. So, we are not talking about general graph spanners, we will talk about only Euclidean spanners. Okay. So, now this quantity, so let me, if I use t equal to suppose 1 plus epsilon, I am just writing t as 1 plus epsilon. So, how does one go about constructing? So, okay. So, what is the advantage of this? Well, there will be an advantage of this only if we have what? Why are we doing all this? This graph, trivially, what can this graph be? The most trivial graph? No. The most trivial graph is the complete graph on these p points. Okay. Just put an edge with the Euclidean distance, then the graph has about n choose 2 edges. Okay. What do we hope to accomplish by relaxing this requirement that the distance can be dilated by epsilon, dilated by 1 plus epsilon. We are hoping to take away some edges from this graph, okay, and still maintain some kind of bound on the distance between 2 points within the graph. Right. So, that is the notion of a spanner. It spans all the points, okay, and someone said a spanning tree. Yes, spanning tree is also going to be a spanner, but then we do not know that what is the t corresponding to the spanning tree. The spanning tree, in fact, you can have a very bad spanning tree where okay. So, just to give you an example, you could have something like this, okay, where you take out one edge, okay, and then you are gone, right. So, the stretch, the t is called often the stretch. The stretch could be very bad, but we want to have a controlled stretch. I will actually parameterize this. I'll supply the epsilon, and you'll have to construct a graph that satisfies this, right? And also somehow not have too many edges. The whole point is not only we should have this bound, but we should also have, we shouldn't have too many edges in this graph. Preferably maybe linear number of edges. Okay, from n choose 2, I want, let us say, close to linear number of edges. You are saying something. That will depend on the epsilon. Yes, that will certainly depend. It's going to be a function of epsilon. So, intuitively, the size of E, sorry, not this. The number of edges, okay, will be some kind of monotonic function of 1 over epsilon. The smaller we want the epsilon, so this will be monotonically increasing or something. It should, the smaller you want epsilon, clearly the more accurate distances, you need more and more edges, and maybe at some point you can't do anything but actually have put all the edges. But epsilon is a real number, let us say between 0 and 1, that is what we are interested in mostly. If it is between 0 and 1, then it is going to increase, but somehow it will be parameterized with epsilon, so that even something like this, let us say 1 over epsilon square times n is also considered linear. Okay. So, it could be something like whatever, so it could be square, could be cube, we do not know really something, okay, and most likely it is going to also depend on the dimension d. Okay. So, perhaps it could be like this. exponential in 1 over epsilon and dimension. So, as you increase the dimension, these things become harder. Okay. Now, it has been pointed out in some of the previous lectures that we already know of one such spanner. Can you? It was a passing remark, but it was noted without proof, of course. So, what kind of sparse graphs do you know about a point set that we have constructed? Yeah, right, very good. So, Delaunay triangulation in 2D, okay, is a spanner with t less than 3. That is what is known. Some number between 2 and 3, and even this bound less than 3, has been improving over the years. Some people have maybe proved 2.77, another person come and said no, it's 2.72. Strictly more than 2 and between 2 and 3. So, people are trying to improve it all the time. Okay. So, there is already something known. So, Delaunay triangulation which has linear number of edges, right. So, you have a linear number of edges, you have a constant factor in the stretch. Okay. So, it is already known. So, in higher dimensions, we want to somehow match that, and not only match that, we want to have a kind of a continuous trade off. I could specify in epsilon. So, this is for a fixed thing, right. I do not have any choice. I have the Delaunay triangulation, but tomorrow if someone said, okay, give me something that has stretch 1.5, okay, Delaunay triangulation does not work. So, we want something more, something general, so that we can actually execute this trade off between the number of edges and epsilon. Right. Also, this is an exercise for you. What falls out of this, out of a spanner. Okay. So, so the claim is, and this is, I leave it as an exercise, that the MST of the graph G corresponding to the T spanner can someone complete this? Well, I mean, no, something in the context of this, So, there is a T spanner. No. Is what is called a TMST of the point set P. So, there is an exact MST. There is an exact MST, okay, which corresponds to the Delaunay edges, which is the subgraph of the Delaunay edges that holds in actually all dimensions. But then I am not interested in the exact MST, okay, because constructing Delaunay triangulations in higher dimensions is kind of nasty, because things grow exponentially. So, I may want to have a somewhat faster algorithm for MST in higher dimensions, okay. And then what do? I could somehow, if I could, I do not even need to use the Delaunay triangulation. If I could construct the T spanner, if I could construct a T spanner, not the T spanner, a T spanner, and I just work on that graph, construct the MST of that graph, that MST will be an MST that is no more than T times the weight of the original MST. Why are we doing all this? After all, a set of points define a complete graph of n square edges or n choose 2 edges, and I can run any kind of spanning tree algorithm on that graph and construct the exact spanning tree. The real interest is that I do not want this n square kind of construction time. I want something much faster, okay. Because these points are in the Euclidean space, I know the geometry, so I want to do something faster. In 2 dimensions, we can do it in n log n time because of the connection with the Delaunay triangulation. As you go higher up, also I want to see at what dimension, how far can I go till I I can get something reasonably subquadratic, okay. And this is one method that people have adopted for that. Okay. So, with this, let me move over to how do we, so what did we start out with? We started out with this notion of well, I mean, can we do something, can we do design algorithm that somehow use the values of the coordinates, okay, and still not be too far away from our notion of optimality, that is, in terms of running time, as well as we are willing to sort of live with a little bit of approximation. Right. So, I will just introduce a definition and then we will take this up later on in the next class. And so I say a pair of point sets Q and R are 1 by epsilon separated if maximum of the diameter of Q and the diameter of R is strictly less than epsilon times the distance between Q and R. You remember I have defined the distance between 2 point sets Q and R. Right. So, geometrically what this means is that I have some point set P, Q, I have some point set R, both define some kind of diameter, maybe these are the 2 points that are furthest apart and these are the 2 points that are furthest apart. Right. Now, I am trying to relate the diameter of the maximum of the two diameters. So, between Q and R, R has the larger diameter and the distance between the 2 point sets is a pair of point, one belongs to Q, one belongs to R. So, maybe this is the distance, these 2 points may define the distance perhaps, okay, the distance between Q and R. Okay. So, this distance must be what am I saying? This distance must be much larger, that is 1 by epsilon times this. So, this distance must be much larger compared to the diameter of Q and R, which is something that we said in the context of when we said that we do this n body simulation. If these 2 point sets are very well separated, that is what basically the separation is. The separation is being defined with respect to the diameter of the point sets. Okay. If they are kind of far apart, okay, then I said you can actually approximate either the distance or some kind of forces or any kind of interaction basically, okay, more easily by some kind of doing a depends on the context, by the center of mass or the or the center of the K median or things like that, so the geometric center and things like that. Okay. So, this is the definition of a 1 by epsilon separated pair. Okay. So, of course, the given set of points may not have this kind of property. Of course, I am given one set of point, I am not talking 2 sets of points. Okay. So, what is that we are interested in? What we are interested in is, given any set of point, I want to somehow partition this set of points, okay, such that I am going to produce some pairs at the end of the algorithm, okay, and each of those pairs should be well separated. Okay. So, this is the last definition. So, And here is a notation. I will just explain this. Union of this particular operator, you can think about it as a direct product operator. Okay. Let me first explain the third part. So, this operator P cross P, or P operation P basically is a set of all pairs of this produced by this set of points. Okay. So, P direct product with itself basically is you take okay, maybe I should do a formal definition. So, A B is equal to union of all x y pairs, x belongs to A and y belongs to B. I think that's a simple definition. Okay. So, P cross P or P operator P defines all sets of pairs, points paired with itself. And I have actually decomposed this set P into this A1, B1, A2, B2 up to A. So, S pairs I have decomposed such that all these point sets are subsets of P. Okay. That's a natural thing. Any pairs of points are disjoint. Okay. And moreover, if you look at the union of all the pairs produced by the individual AIBIs, okay, they contain all the pairs of the original point set. And in addition, if I can guarantee that AIBI are 1 by epsilon separated. Okay. So, this decomposition is then called the epsilon well separated pair decomposition, or epsilon WSPT. So, this is what basically we will take up next time, and we will show that this way of decomposing points has applications to many things, including the ones that I just mentioned today.